In this lecture, we will see about the stationary state and their linear combination. This is revised and updated one. I have already given one lecture on stationary state. Here, in addition, I am going to give about the linear combination of stationary states. This is revised and updated one. Now we will see the separation of wave equation. The Schrodinger equation is IH cross partial derivative of capital psi x t. This capital psi represents the wave function depends both on x and t. So we are taking partial time derivative of this wave function, which is equal to minus h cross squared over 2m delta 2 psi x and t over delta x2 plus v of x psi which is a function of x and t. Here you should remember that this vx is only the function of depends only on the position, not on the time. So that assumption we are taking up. Now you substitute this. You separate the wave function into two parts. That means the capital psi x of t, x and t is equal to small psi of x multiplied by small pi t in the above equation. Here, psi depends only on x and pi depends only on t. So we are separating the wave function into two parts. One is the position part and the other one is the time part. Now you replace here. In the left hand side, since it's a partial time derivative, there is no time dependence on psi. So we are differentiating only the pi. Similarly, in the left hand side, you can see this psi depends only on c. We are taking partial derivative with respect to x. So naturally, the psi alone depends on x. So we are taking pi outside because there is no position dependence on pi. So now you divide this above equation by capital psi, which is a function of x and t, which is equal to psi of x and pi of t. So if you uh, divide this by the total wave function, that is psi x pi t. Here psi x will get cancelled because we are dividing by this factor. So only pi of t remains as psi of x cancel out. Similarly, in the right hand side, the psi of t will get cancelled. You will get only, sorry, pi of t will get cancelled. You will have only psi of x. So, with this understanding, we will move further. Now we got this expression, that is IH cross 1 over pi, the partial derivative of pi with respect to t is equal to minus h cross squared over 2m delta 2 psi over delta x2 plus v of x psi of x, the whole thing multiplied by 1 over psi of t, sorry, psi of x, psi of x. You can see that this left hand side purely depends on the time t, and the right hand side purely depends on x. So if you are changing the time, it will affect only the left hand side. Right hand side does not have any effect because there is no time dependence. So naturally, In similar way, if you change x, only the right hand side will change. It will not affect the left hand side. So naturally, uh, both will have a common constant. That constant we are designating as E, that is energy. We can prove it, but right now you take that constant is E. So you first take the right hand side, which is equal to E. Then you bring this psi of x to the right hand side, then you will get the Schrodinger wave equation, um, minus h cross squared over 2m. Uh, Now remember that here I have converted this partial derivative into full derivative because it's purely depends on x. There is no time dependence. So I have converted this partial derivative into full derivative. So that also you have to keep in your mind. So if you bring this psi of x to the right hand side, you will get minus h cross squared over 2m t2 psi of x over tx2 plus v of x psi of x, which is equal to e psi of x. This is the Schrodinger wave equation. That is time independent Schrodinger wave equation. There is no time dependent in it. Then you take the left hand side. That is I h cross over pi uh, t pi t over tt. Here also I have converted this partial derivative to full derivative because here all parameter depends only on time. So partial derivative will become full derivative. This left hand side, as I said, it's exactly equal to E. By taking the left hand side, we got this expression I h cross over pi is equal to t pi over tt, which is equal to E. Now you bring this pi to the right hand side and I h cross also to the right hand side. This I h cross can be equivalently written as minus I over h cross. Uh, so, simply if you multiply and divide by I, you will get I squared is minus 1. So, this will become plus, and here you will have I h cross. So, generally, when I h cross, if you brought the I h cross to the other side, it will be written as minus I over h cross. Then the equation for pi of t is readily integrated to q. Pi of t is equal to e power minus I e t over h cross. If a is normalized, then a is equal to 1 if it is normalized. Then it can be simply written as e power minus I e t over h cross. So the total wave function can be separated into two parts, as I said, psi of x, pi of t. So now we got the value for pi of t is this exponential term. So this can be written as psi of x, small psi of x, e power minus I e t over h cross. From the above wave function, that is from this wave function, you can write this. That is, if you uh, differentiate this, that is, psi, total wave function, which is psi of x e power minus I e t h cross. If you differentiate this expression with respect to time, in fact, this is a partial derivative because it depends on both the x and t. So I h cross partial t psi by dt is equal to I h cross. Uh, that is this I h cross I am keeping as it is. If you differentiate the total wave function with respect to t, psi of x, there is no time dependence, so I am keeping as it is. Then what about the exponential term? This exponential term, if you differentiate, you will get minus I e over h cross. So that I have written here. Then and that exponential term I am keeping as it is. Now some modification. Here this H cross and this H cross will get cancelled. Similarly, this I here one another I squared is minus 1. So this will become plus. So here the left out term is only E. And this remaining thing. This is the total wave function. We know this is the total wave function. Psi, capital psi of x and t. This is a total wave function. You can see it here. So this will be equal to E capital psi. So just now we got this equation, that is IH cross partial time derivative of capital psi is equal to E capital psi. Psi is the total wave function which depends on x and t. So we are taking partial derivative. This equation is called eigenvalue equation. This blue color is an operator. A parameter shown in blue color is an operator. That is IH cross delta over delta t. When it acts on the capital psi, it gives the energy eigenvalue E with its wave function capital psi. So that is this is the wave function. So this is the eigenwave function, we can say. So this eigenfunction, when this operator IH cross delta over delta t act on the wave function, it gives the eigenvalue of E. This is the eigenvalue E. So this psi, capital psi is called eigen function. As I said, this is called eigenvalue equation. So the operator, energy operator is IH cross delta over delta T. We have also seen that uh, minus H cross squared over 2m delta 2 over delta x2 capital psi x and t plus v of x into psi x and t e which is equal to e psi x and t. In similar manner, what I claimed here, psi capital psi x of t is also eigenfunction of the operator with the same eigenvalue. That is, you take capital psi as a common, then remaining thing is minus h cross squared over 2m delta 2 over delta x2 plus v of x. This is the operator. You remember that this is called Hamiltonian operator. We have used quantum mechanics very frequently about uh, this Hamiltonian operator. Now we will see the significance of the separation constant E. Uh, we have taken that total wave function capital psi, which is a function of x and t, is separated into two parts. That is, it is equal to psi of x. We have seen throughout this lecture psi of x and the time dependent e power minus I e t over h cross. This is the radial part. This is time part. Now you take psi star psi. So now psi star is that is a small psi complex conjugate. Psi star is this plus will minus will become plus. Psi star multiplied by psi. So here your psi is this one. So psi I am taking as it is. Then, since this exponential term is a constant, you can bring back and forth. So I have brought this to the brought this after this psi of x. So this will become psi star x psi of x e power minus I e t. This I brought to the last because it's a constant, so you can change the constant. You are not supposed to change the order of the operator, but you can change this. So here e power minus theta into e power plus theta I theta. This will be equal to 1. You know very well. This is equal to 1. Then this will become psi star psi, capital psi star psi is modulus psi square. Similarly, this small psi star psi is equal to modulus psi of x whole square, because it is exponential term will become 1. See here in the right hand side you have time dependent, but what about left hand side? There is no time dependence. So both are equal. That is, the probability of finding the particle is independent of time. There is no time dependent. So an energy eigenfunction like the capital psi in the above equation is said to be represent a stationary state of the particle. Since the modulus square of psi is a constant in time. So that is the significance of the separation constant E. This is the case for a single wave function. Now we will see what will happen if you take the linear combination of it. That is the important point in this lecture. Uh, just now we have seen that the probability of the finding the particle for the wave function psi, which is a function of both position and time, is actually the probability is independent of time for a single wave function. Now we will see what will happen if there is a linear combination of or more wave functions. We will take a simplistic case that two stationary states. Suppose a particle start out in the linear combination of just two stationary state. Capital psi of x at time t equal to 0, that is important, t equal to 0 is equal to a1 psi 1 of x plus a2 psi 2 of x when time t equal to 0. We have just now seen even when time t equal to 0, if it is a single wave function, it is the probability is a time independent. Now we will see this. Because it's a single wave function is time independent, we are calling it as a stationary state. Here, this is at time t equal to 0. For a particular time t, then it will be written as rewritten as a1 psi 1 of x e power minus e1 t over h cross plus a2 psi 2 of x e minus I e2 t over h cross. So this is the linear combination with time. If it is single wave function, as I said, it is probability is independent of time, so it's called stationary state. Now we will see what will happen for the linear combination. So now you take the modular square of this wave function, then you take modular square of first wave function. That is, this will be a1 squared psi 1 squared. Because if you take complex conjugate of this exponential term, e power minus will become e power plus, so that will become 1. Similarly, for second one individually, it is a1 squared psi 1 squared. Because this is minus e power minus I e2 t h cross. If we take complex conjugate, this will become plus. So if you multiply e minus t into e plus t is 1. So this also individually 1. Now you multiply this and this because you are taking the modular square. Then this will become a1 a2 psi 1 star psi 2. So psi 1 star, this will become plus e1. So I am rewriting psi 1 psi 2 is minus e2. So I am replacing the exponential term e power minus I e2, because this is automatically become minus e2. this will become plus E2 because already there is minus outside. Minus of minus will become plus. So this can be written as when you do the cross multiplications, wave function 1 and 2, then A1, A2, psi 1 star psi e power minus I E2 minus E1 t over H cross. Similarly, if we take this psi 2 psi 1, if you multiply this, that is psi 1 multiplied by psi 2 star. So you take complex conjugate of this one. If you take complex conjugate of this one, E2 will become plus. So this exponential term e power I E2 minus E1. So times t over H cross. This is the modulus square of the total wave function. Now we have seen this equation. You add last two terms, that is uh, third term and fourth term. That is, I will use different color. So we will add these two. Then, because here psi 1 and psi 2, small psi 1 and psi 2 purely depends on position. So psi 1 star is equal to psi 2. Similarly, here psi 1 star, psi 2 star equal to psi 2. So we can take A1, A2 and psi 1, psi 2 as common factor. A1, A2, psi 1, psi 2. So then you can take this exponential term. So this is replaced by this one. We have combined the third and fourth term. So here, what is e power minus I theta into e power I theta? That is equal to 2 cos theta. That's what I used. I used the fact that this is this third term, except A1, A2, psi 1, psi 2. This thing, this bracket terms in the curly bracket is equal to 2 times cos E2 minus E1 t over H cross. So you can see first term independent of time, second term independent of time. What about third term? Third term is a oscillatory one because there is a time dependence. So here the omega is equal to E2 minus E1 over H cross. So it will have oscillation with the frequency E2 minus E1 over H cross. This is the angular frequency. So naturally, the linear combination of two stationary state is not a linear one. It's a oscillatory one. This you cannot call it as a stationary state. If you take these two separately, then it is a stationary. If you take linear combination, then it is not a stationary, it's a oscillatory one. So now we will see what is this A1, A2. We will see what is A1, A2 and their importance. Just now I told that A1, A2 are the probability amplitude. The total wave function can be written as a linear combination of so many wave function with a probability amplitude an. This can be written as summation over n, which is between 1 to infinite, an of an times psi n, which is a function of x and t. This capital psi n can be written as small psi n, which is a function of x. That's what we have seen so far. Multiplied by this exponential term, that is a time dependent term. Now, what is the expectation value of Hamiltonian? This an, the square of this probability amplitude is probability. Modulus square of the probability amplitude is basically the probability amplitude is a complex number. So modulus square of that gives the probability. That is the expectation value of Hamiltonian, that is total energy, is equal to the summation of uh, n is equal to 1 to infinite modulus an squared en, where an squared modulus an squared is probability of finding the particle at the nth state. So each state we have by a particular property. For example, E1 you will have particular property, E2 at some other property, E3 some other property. It will go on. So each energy state will have some probability. Naturally, the total probability must be equal to 1. Summation over 1 to infinite modulus an squared is equal to 1 because total probability is 1. Now you can understand the probability amplitude. So which gives you the probability of the finding the particle at a particular energy state. Thank you very much for watching my video and supporting me continuously. Thank you.